the things are made up of atoms, then why everything is different? Okay, why there is like a door which is a wood, why we have metals, why we people are different? Everything is made up of atom, right? All the atoms are the same electrons, protons, and the nature of electrons, protons, neutrons are same. But then the sparks that were coming out from the welding, I decided right on that spot that my mom might even when they cook food in the kitchen, I don't see the sparks coming out. Although the pans are sitting on the stove, they are giving the same amount of heat, but sparks does not come out. But what is that specialty that is in that piece of welding piece which is not in present in the kitchen cooking wraps? You see rainbows all the time. Okay, why is that when it rains then only you see the rainbows? Okay, or why is that when you have a scale, and if you put the scale in front of a light, it's split into different colors, multicolors? Okay, so try to put this kind of questions into the minds of the children.
I have heard some people, I mean, very knowledgeable people, actually relate this quantum mechanics, quantum physics with spirituality, right? Because, I mean, the universe exists, but it does not exist.
We have to understand that quantum mechanics itself is a framework. Okay, it's a framework where you want to know the properties of some quantum particles, so very elementary particles. Okay, so then Sudeep, I would say that you really have to know the difference between this. I mean, to appreciate quantum mechanics, again, I would say that you have to know the difference between the classical mechanics and the quantum mechanics. But in quantum world, you are not able to see the things. Okay, in the quantum world, the electrons are so tiny things, you cannot even hold it. So when you cannot see the things, when you cannot hold the things, how can you explain the things? Okay, so that's the thing. So that's the difference between the classical mechanics and quantum mechanics. In quantum mechanics, when you don't see a thing, it does not possess any property. Max Planck, okay, Max Planck in the year 1900, he came up with the idea. Actually, he coined the word quantum first. Okay, so how did he come, or how did he brought this subject? Okay, earlier it was just Newtonian mechanics, some other mechanics, okay, but not electrodynamics was there. Okay, these were very old. I mean, but the quantum mechanics is something which came in this 1900.
So, you are doing research on quantum materials, right? So, can you explain to us what that is? What are quantum materials? We cannot see those materials, right? So, how are you doing those experiments?
Quantum is a very, it's a very interesting thing. Only due to the fact that you are not able to see the elementary particles. Okay, and as a result, in the year, I believe, Louis de Broglie, Schrodinger, Heisenberg, these are the very famous scientists that came in the year around 1925, 26, 27, back to back. They gave a solid foundation of quantum mechanics. So quantum mechanics says that it's all about probabilistic. It's a probabilistic approach. Classical mechanics is more deterministic approach. You can determine exactly when the bus will reach. But in quantum mechanics, it's a wave approach which can probably tell you that where the particle is. It cannot tell you exactly where the particle is. In many areas, spiritually, people have said many things much ahead than the scientific discovery. It has happened. Okay, but then in both the cases, the one thing is common, that in both the cases people have believed on something. What people have found is that when you go from bulk to thin layer, atomic thin layer, the property starts changing. Okay, so that means, for example, if I go by electrical property, in the bulk layer, let's say it was insulating. Okay, but when I went to atomistic layer, a thin atomistic layer, it became superconducting. These kind of materials can be seen through naked eye. I mean, it's clearly visible. Okay, so I can say that instead of this gold, I can come up with this WSE2 ring. Okay, so if I bring it to you, I can show you, Sudeep, see, this is a WSE2 ring. You can feel it, you can touch it, you can do anything. Okay, it's a solid structure.
If Einstein was alive today, seeing the progress that we are making in quantum, what would he think?
If you talk about leisures, if you talk about smartwatches, if you talk about kitchen microwaves, if you talk about washing machines, everything you have this small controller, microcontroller, which is governed by this quantum mechanics, principles of quantum mechanics. Understand one thing, that this quantum uh, information, it has four pillars basically. Okay, it has quantum computing, it has quantum communication, it has quantum sensing, and it has quantum materials. Okay, so these are the four pillars. So China is undoubtedly the sole leader of the quantum communication part. But yeah, I mean, this is what the today's youngsters have to look for. I mean, yeah, if you want to understand quantum mechanics through a movie, through a comic show, or through some simple experiments, do it, go for it. Okay, so this scientific department needs to build up within this young community, I mean young students, just not rushing for marks, for clearing these competitive exams. This won't work.
Hello, everybody. This is Sudeep here. Welcome back to my channel once again. In today's podcast, I am talking to Sri Rupam Mukherjee, who is a professor in the Presidency University of Bangalore and also is a researcher of quantum materials. In this podcast, I got to learn a lot of things about quantum. And if you are interested in quantum, this podcast is for you. But before we get started, I have one request for you as usual. Please do like, share, and subscribe to this channel so that I get the motivation to keep bringing on such videos for you. So, with that, enjoy the show. Thank you, Rupam, for coming on the show and really appreciate your gesture and giving me time to record this podcast. Um, I think it will be a wonderful podcast because a lot of people want to know about quantum because I feel that that is the next wave of technology after this like wave of AI subsides in a few years' time. So a lot of people want to know about quantum, and with your kind of knowledge, I think this will be an exciting podcast for me and also for the viewers. So, having said that, we'll get started now. And at the start of the podcast, I would request you to please introduce yourself to the viewers, starting from how your journey has shaped up, like your childhood, what kind of like education did you do, and then how you landed up into quantum like research and all those kinds of things. If you can briefly take us through that journey.
Okay, Shudip, thanks for inviting me. I really appreciate your effort. Um, so to begin with, I was born and brought up in a town called Burnpur. It's a part of Asansol, West Bengal. So my schooling started, or my schooling, I completed my schooling over there only. I mean, the school was like 500 meters away from my home. Thereafter, for my bachelor's, I went to Calcutta University. I joined Belu Ramakrishna Mission Vidya Mandir. It's affiliated to Calcutta University. There, I got enrolled into physics honors. After that, after completing the degree, I went to IIT Guwahati to pursue my master's. Um, and then to fulfill my dream, that is to pursue my PhD, I went to United States. There, I joined Wayne State University, Michigan. I completed my PhD in 5 years, and then finally I moved to University of Tennessee, Knoxville, in US for doing my postdoctoral activities. So in postdoctoral, I did my postdoctoral for approximately 4 years, and then eventually we decided, my family decided that we should come back, and then we came back to India, and then after that I joined some other private universities, and now I am at Presidency University, Bangalore. This is also one of the private organization, but here I have joined as a research assistant professor, where mostly you have to focus mostly on the research part rather than on the teaching part. So this is what my journey, I mean, looks like. But frankly speaking, I mean, although it might sound sweet, but there were a lot of struggles. I mean, nothing came easy to me. But anyway, due to the blessings of my parents, my cooperations from my own families, my wife, my son, blessings from God, I am here today.
Yeah, so like with I was actually reading a book, uh, which is a conversation kind of thing with uh, actually between Dalai Lama and the South African Archbishop, right, Desmond Tutu, where
Correct.
they were also speaking that nothing sweet comes other than struggle, right? If you don't struggle, you don't get success. So it's an universal law. So I totally relate to what you are saying, and it's wonderful to have you and see you successful after such struggles and whatever you spoke about, right? So all the best and
Yes,
for your
correct.
future, and
Yeah.
congratulations on achieving what you have achieved so far. Okay.
Thank you, Shadi. Thank you.
Okay. So let's move to the exciting topic now, which is quantum. So when you first heard about quantum, right? Obviously, you started as a student of quantum, right? Everybody starts on a student, like as a journey as a student in a particular subject, and then he becomes expert, which you have become now, uh, like over the course of time and all that. So when you first heard of the term quantum, what image came to your mind as a student at that point of time? If you can take us through that journey.
Yes, Shudi. Frankly speaking, I mean, this is a very tough question, okay? Because I mean, it was not a instant thing that happened overnight. As far as I remember correctly, like any other students of my age, when I was in eighth standard, I was exposed to these quantum particles called electrons, protons, neutrons, and so on. Who discovered electrons? That were the mere topic. I mean, these were the topics that were taught in the class. But then, I mean, I would not hesitate to say that the actual beauty of quantum mechanics I came to know when I was at the end of my PhD. Okay, so it was a like a decade journey to understand what is quantum mechanics. But frankly speaking, when teacher came and taught about these electrons, protons, at the end of the class, I still remember that he said one thing, that everything which you see around yourselves is made up of atom. So that was the statement he made. And uh, and then after that, after listening to that, when I came back home, I started asking these questions to myself, that if all the things are made up of atoms, then why everything is different? Okay, why there is like a door which is a wood, why we have metals, why we people are different? Everything is made up of atom, right? All the atoms are the same, electrons, protons, and the nature of electrons, protons, neutrons are same. So this, I mean, this kind of questions actually intrigue me to look for some other extensive knowledge. I mean, I started asking my parents, I started asking my immediate teachers, and they told me clearly that when you grow, I mean, when you go to class 12 standard or 11 standard, you will start knowing these things. Okay, so yeah, I mean, quantum is something. I mean, I would also try to say these things to, I mean, students. This is entirely my opinion, that in order to appreciate quantum, you have to know the fundamental laws of nature. Okay, for example, the Newtonian's law, the gravitation's law. Okay, so until and unless you don't appreciate those classical laws, okay, you cannot understand the quantum better. So very first time when I was exposed to this word quantum, when I was in class 12 standard, particularly this word quantum, I remember I had this chapter. So I took that chapter as a part of syllabus. I mean, nothing special to me. Okay, I just, since it's a part of syllabus, I have to finish it, and then I finished it. Okay, but later on, when I finished my class 11 standard, when I went to class 2 standard, and then, but then after even going to college, I decided to take the, I mean, take the notes or to gather the books from the 11th 12th standard and revisit the quantum thing again. Okay, so this is how I slowly and slowly built the interest of quantum. But I mean, it was a good thing. I mean, asking questions continuously. For example, I still remember this incident, when my bicycle broke. One of the pedal got broke. My father insisted me to take to the repair shop, and then when I took the cycle to repair shop, I saw, he suggested me that he will weld that part, welding. Okay, and then he started welding it, and he fixed it in 5 minutes. Okay, but then the sparks that were coming out from the welding, I decided right on that spot that my mom, my even when they cook food in the kitchen, I don't see the sparks coming out. Although the pans are sitting on the stove, they are giving the same amount of heat, but sparks does not come out. But what is that specialty that is in that piece of welding piece, which is not in present in the kitchen cooking wares? Okay, so this is how my journey started. Okay, um, but but it was a, I mean, if you try to understand word quantum, okay, I would suggest everyone that try to relate the things with the knowledge which you already have. If you are going for some explanation, so let's say if you want to explain some phenomena with the knowledge which you have, for example, the fundamental knowledge or the classical knowledge, if it doesn't fit, then you should ask some more serious questions to yourself. And this is how you propagate, or this is how you make your path.
Okay. So, interesting question. So, you are a professor, right? And let's assume that I
Yes.
am a 10-year-old kid, right? I do not know anything about quantum. So, how would you expose me to quantum and how would you explain to me what is quantum, right? I am just a 10-year-old kid and I want to know what is quantum from you. So, in simple language for our viewers or whoever is watching, assume them as 10-year-old kid and explain to them what is quantum.
So should it again? If you really want me to make understand a 10-year-old kid what is quantum, I will leave. I will leave him alone. Okay. Let him have enjoy his life. But jokes apart. Um again, the children of that age, 10 years age, you can start relating the quantum with the phenomena which they are seeing. For example, why you can try to explain that, do you see rainbows all the time? Okay, why is that when it rains then only you see the rainbows? Okay, or why is that when you have a scale, and if you put the scale in front of a light, it's split into different colors, multicolors? Okay, so try to put this kind of questions into the minds of the children, rather than trying to explain what is quantum to that 10-year-old kid. Okay, and I believe these kind of questions will that the thought process should initiate within the brain of that child. Okay, if he's serious about the if he's serious about these questions, and automatically he will try to ask you some counter questions. Okay, and in that way the children interest can build up. Okay, but explaining quantum directly to 10-year-old kid or anyone of that age will be little difficult. You need to have uh, I mean, those, at least to a students, a college going students who had a little exposure on quantum mechanics in class 2 standard, class 1 standard, you can take them to little different level. Okay. Yes, that is what I can say.
Okay, okay. So then let's move on to something else then, right? So when a
Yeah.
student comes to you, right, and he is, let's say, interested in quantum and has read a little bit about quantum and he knows something and he has some questions. So there are some basic theories of quantum, like that slit experiment, things do not exist, and all those kinds of things. Whatever little knowledge I have gathered, I'm just sharing. You are the professor. So now you explain to me what are the basic theories of quantum in a simple language for our viewers, two or three theories that are there, if you can explain that.
Okay, great. So if I have to start with the quantum, we have to understand that quantum mechanics itself is a framework. Okay, it's a framework where you want to know the properties of some quantum particles, so very elementary particles. Okay, so then, Sudeep, I would say that you really have to know the difference between this. To appreciate quantum mechanics, again, I would say that you have to know the difference between the classical mechanics and the quantum mechanics. For example, when we talk about the classical mechanics, or when you, classical mechanics is all about the phenomena what you see in the macroscopic world, or how the body behaves in a macroscopic world. Okay, for example, in classical mechanics, the object which we speak about, whether it's a chair, it's a table, it's a laptop. Okay, so the properties that possess, whatever properties that objects possess, okay, is there. Irrespective of any measurement, you have to understand that whether you measure it or not. Let's say this piece of mouse will have a mass, because every body is made up of a matter. Okay, this is a macroscopic object, but in quantum world you are not able to see the things. Okay, in the quantum world the electrons are so tiny things, you cannot even hold it. So when you cannot see the things, when you cannot hold the things, how can you explain the things? Okay, so that's the thing. So that's the difference between the classical mechanics and quantum mechanics. In quantum mechanics, when you don't see a thing, it does not possess any property. Although, irrespective of the measurement, until you do the measurement. Okay, for example, the electron, whether it is spinning in clockwise direction or anti-clockwise direction, you will never know until you measure the thing. Okay, but the color of this mouse, whether you see, I see, she sees, or whoever sees, is always black, isn't it? Okay, so this is the main difference between the quantum mechanics and the classical mechanics. Another important thing is that when we are talking about these elementary particles, okay, there, these quantum particles, the world of quantum mechanics is totally, it has an inherent fuzziness in this system, in this quantum universe. Okay, for example, there are many things even in the past people have found. For example, Max Planck. Okay, Max Planck in the year 1900, he came up with the idea. Actually, he coined the word quantum first. Okay, so how did he come, or how did he brought this subject? Okay, earlier it was just Newtonian mechanics, some other mechanics. Okay, but not electrodynamics was there. Okay, these were very old. But the quantum mechanics is something which came in this 1900. Okay, so what Max Planck has observed in his experiment is that he was doing spectrum studies on black body radiation. Okay, black body is something which can absorb or emit any amount of, or any wavelength of light. So then what experimentally he's observed is that when the wavelength, or when the frequency increases, frequency of the emitted spectrum increases, the intensity drops. But in classical mechanics, you don't see the drop. Classical mechanics says that when you increase the intensity, or when you increase the frequency, the intensity will increase, or it can go to infinite. But then experimentally, he found that no, it's not going infinite; it's dropping. Okay. Then he came up with the theory that the emitted electromagnetic spectrum from the black body is basically comes in a discrete form of packets called quanta. Okay, so you see, again, for him also, he wanted to explain the things from the knowledge which he had, but then something did not fit up. So then he formulated a new formalism or new theory which is called the quantum theory. Okay, the similar thing happened with many other people. I mean, as you took a example of the double slit, Young's double slit experiment. Before Young's double slit experiment was, he actually wanted to prove, or he wanted to show the wave nature of these electrons. Okay, I will come to this part. I mean, there were, I mean, certain revolutions took place around 1920s, which came up with many interesting ideas. For one of the idea was elementary particle can behave both as a, or elementary matter can behave both as a particle and wave. Okay, but Young's, he did his experiment. I believe he did his experiment in the year 1870. I believe Young's double slit experiment. Okay, but he wanted to show the wave nature of those wave nature of the light. Okay, but before that, some corpuscular theory came up. Okay, corpuscular theory says that photons, not photons, the light is basically made up of tiny particles which travels in straight line and so on. So okay, so science is indeed kind of a baby steps, okay, to establish one, or to establish the foundation of quantum mechanics. It never happened overnight. People from 17th century, people from even 16th century, they started Dalton. Okay, Dalton came up with the idea of the atom. Okay, so these are all quantum particles, and you see the journey. Okay, so I mean, quantum is a very, I mean, it's a very interesting thing. Only due to the fact that you are not able to see the elementary particles. Okay, and as a result, in the year, I believe, Louis de Broglie, Schrodinger, Heisenberg, these are the very famous scientists that came in the year around 1925, 26, 27, back to back. They gave a solid foundation of quantum mechanics, that if we are now satisfied that all the elementary particles indeed behave as wave also, then let's formalize a new mathematical treatment how to represent such waves in quantum mechanics. Okay, and this is how the story went on. Okay, so now you can deal electron as a particle, which Einstein did. Okay, Einstein, what was the Einstein's experiment? His 1905 paper on photoelectric effect. Okay, it was basically he tried to extend the idea of Max Planck and incorporate it in his work. And later he found that, or he concluded that photons, or those lights, are made up of tiny elementary quantum particles called photons. Okay, so you shine the light on a particular material, and from that particular material, those electrons will come out, and then those electrons can be used to conduct electricity, okay, or photocurrent. But again, you see Einstein's actual photoelectric effect. I mean, he gave the actual theoretical explanation of photoelectric effect. But then, way before Einstein, there was a scientist called Heinrich Hertz. Okay, Heinrich Hertz was the first one who actually observes the photoelectric effect. Okay, and he saw that the sparks that is coming out from the zinc plate, when he irradiated the zinc plate with the UV light, some sparks starts coming up. Okay, and at that time, I mean, at that time, quantum mechanics was not known to anyone. But luckily, Einstein took his work and then repeat the experiments, and then he explained successfully. And then later he came up with the fact that the light which we are indeed seeing is basically a quanta of particles, okay, which is called photons. Okay, so quantum world is very different world, Sudhir. I would say that, I mean, as you asked me that how do you explain to a normal students, or normal any normal person from any background of life, I would say that you can take an example of, let's say, a bus. Okay, a bus on a road. Okay, if you know the position of the bus, if you know the velocity of the bus, you can 100% says that at what time the bus will reach to your home, or at what time the bus will reach to your office. Let's say if the bus does not break down, or if the bus does not I mean, experience any hardware problems. Okay, but in quantum mechanics you cannot do that. Okay, because it's a wave which you cannot hold. Okay, So quantum mechanics says that it's all about probabilistic. It's a probabilistic approach. Classical mechanics is more deterministic approach. You can determine exactly when the bus will reach. But in quantum mechanics, it's a wave approach which can probably tell you that where the particle is. It cannot tell you exactly where the particle is. Okay, here comes the picture of the Heisenberg. Okay, Heisenberg actually gave the same thing. Okay, Heisenberg's paper, he gave the Heisenberg was known for he was known for two things. One was he developed the quantum mechanics in a matrix form, and the other part is the Heisenberg's uncertainty principle. We have been reading these Heisenberg uncertainty principles ever since we were in class 9 standard or class 10 standard. Okay, maybe little one sentence was there, and in 11 standard or 12 standard more broad sentences were there. Okay, so Heisenberg uncertainty principles clearly states that you cannot measure the electron's position and the momentum of the electron simultaneously. Okay, as if you can relate these things with the classical world. For example, in the fair you might have seen people blowing bubbles, right? You might have seen people blowing bubbles. Okay, if you try to catch the bubble, okay, the more you try to go towards the bubble try to flies away. Okay, so that's the thing. Okay, so quantum is something which is already present in the nature. Okay, so Heisenberg uncertainty says that when you try to determine the positions of the electron accurately, you basically you basically lose control of the momentum of the particle. Okay, and there was indeed one experiment. There was a tiny hole made in a plate, and on the other side of the hole, you flash a light. You flash a light from the hole through this hole, and then you will indeed see that it's just not a spot on the screen which is coming up. Rather, it's a kind of a broad, delocalization of the waves. Okay, but again, you see in the classical picture, if I have a gun and if I shoot the gun from through this hole, okay, you can 100% say that this is the area of the wall which will get affected by the bullets. It's the same area as the area of the hole. But in the quantum mechanics, if you shoot an electron through this hole, okay, it's just not only on that central spot, you will also have some patterns on the sideways. Okay, both right and left of the central portion. Okay, this is what quantum mechanics is. Okay, you cannot explain these things with the help of simple classical knowledge. You understand what I'm saying?
Yes, yes, very interesting. So, I have heard some people, very knowledgeable
Yes.
people, actually relate this quantum mechanics, quantum physics with spirituality, right? Because,
Okay.
the universe exists, but it does not exist, right? Until you observe it with your eyes, right?
Correct.
God
Correct.
exists,
Correct.
God does not exist until you look at that image, or you get that feeling, whatever. Different people have like different notion about that. So how do you feel about it? Is it really that strange that if we do not observe something in this universe, that's what is fundamentally quantum, right? If we do not observe something, it does not exist. Or if we cannot measure something, like you said, right, it does not actually exist, right? That's what is quantum, and that's what is human belief. That's how spirituality also works. That's how the basic principles of the world also like evolves around, or revolves around, right? So am I right or wrong? Like, what's your thought on that?
But Sudip, this is a very very good question. Okay, I am not expert in this field. Okay, indeed I have seen people relating science with religion. Okay, as you said that even the God is not visible to us. So is it a quantum object or things? It's all a matter of belief. Okay, even quantum mechanics. If you see the evolution of quantum mechanics, okay, the evolution of quantum mechanics also started with the with certain beliefs that something is there beneath the surface. Okay, we have to identify the things beneath the surface. Okay, so beneath the surface means, I mean, when you are going to that atomic level. Okay, so I would say that again, it's a the building up of a universe. Whether it's people have been trying to find these Higgs bosons, or famously known as God's particle. Okay, it all depends on one person. Okay, I mean, if you try to see that particle as a God particle, you can think that God as, you can think of, let's say, I mean, it's a God who has created the universe. And but if you think that boson particle simple as a quantum particle, you will be more scientific. You want to explain the things from the scientific point of view. Okay, so even, I mean, you can have a clash, or you can have an overlap of these two concepts. Okay, in many areas, spiritually, people have said many things much ahead than the scientific discovery. It has happened. Okay, but then in both the cases, the one thing is common, that in both the cases people have believed on some things. Okay, even in the case of religion, people have believed that he or she or the God is there. Okay, so until and unless you don't believe on the so again, one thing, you, so belief does not means that you should not question. Okay, belief, so when you believe on some things, many people stop questioning. Okay, when you stop questioning, you stop evolving. But when you believe on something, again, ask some counter questions. Okay, if that is there, then they must also exist. If that is, if they exist, how can I reach there? In that way, you can develop these things, I mean, this connectivity. Okay, but this is a kind of I mean, this is my opinion, I would say. People can have other opinions too. They can strongly relate religion with science, but for me, it's a kind of independent thing. Religion is in a separate thing, and science is a separate thing, in different domain.
Okay, that's fine. So, you are doing research on quantum materials, right? So, can you
Correct, correct,
explain to
correct.
us what that is? What are quantum materials? We cannot see those materials, right? So, how are you doing those experiments?
Yeah, that's good question, Sudhir. I mean, quantum materials, we can see those quantum materials. It's not that, I mean, we can create the materials. It's just the property of the electron. So you are changing the environment of the electrons. Okay. So for example, this cup also have electrons. Okay. It has protons, it has atoms and electrons. But this is not a quantum object. Okay. When we say quantum, um, I would say that it has two roots. One of the root is to just to understand quantum from the size point of view. Anything which is of nanometer size, Armstrong size, you can just straight away say that it's a quantum. The other part of the quantum is more interesting. Okay, so that means how you can change the environment of the electrons. Okay, for example, if this is a ceramic, if there are carbons, it can have polymers. If there's hydrogen bonds, there's a carbon bond, and so many things. Okay, but the electrons, I can manipulate the environment of the electrons around the carbon atoms. Okay, this is what actually graphene came up with. Graphene was indeed a quantum material which was discovered in 2004. Okay, it was discovered in year 2004, if I'm correct. Yeah. Okay, so what is the specialty of the quantum material? Quantum material is something which is kind of an atomic layer thin material. Okay, you see, this is not an atomic layer thin material. It has a thickness. It has if I cut this cup in cross sections, there are bunch of planes of atoms. There are so many bunch of planes of atoms. Okay, but in those quantum materials, you can have actually a layer of atoms, a single layer of atoms, or a double layer of atoms. So layer by layer, you can choose, or you can create that quantum materials. Okay, so earlier the electrons in a 3D world, or in this 3D topography, the electrons can see hydrogen, electron can see some bonds with other nearest neighbor carbon atoms and so on. But in the 2D materials, or in the quantum materials, they have their only nearest neighbors in their own plane. Okay, they can have certain bonding between first layer and the second layer, but these layers are very weak bonded. These are called the van der Waals bonded layers. Okay, the bonding in between this intra layer or in this inter layer is called van der Waals bondings. Okay, so quantum materials, yes, I did work on quantum materials. For example, this tungsten diselenide WaC2 MoS2. Okay, so why they're unique? Because I mean, you see, you can create a 3D quantum material. Okay, again, don't go by the fact that it's an elementary particle, I cannot see that. I'm not talking the, or I'm not taking the particle, or I'm not taking the material from the from the atomistic size. Okay, so you can create that particle, or you can create that structure, 3D structure, by some synthesis process, and slowly you can thin down the, slowly you can thin down the thickness of the material, and then eventually you can land up having just one atomic layer of that quantum material. Okay, for example, WaC2, or one layer of, or two layers of MoS2. Okay, so interestingly, what people have found is that when you go from bulk to thin layer, atomic thin layer, the property starts changing. Okay, so that means, for example, if I go by electrical property, in the bulk layer, let's say it was insulating. Okay, but when I went to atomistic layer, a thin atomistic layer, it became superconducting. But if I do with this cup, this is an insulator. But if I break it into two pieces, and again if I measure it, it will still be an insulator. There's nothing interesting thing in it. Okay, so why these properties are changing? Because you can understand, when you are dealing with this atomic thickness, I mean atomic thinness, I mean this layers of atomic layers, you are basically having the wave functions of those. If you remember that each elementary particles also behaves as wave. Okay, so you can understand that there are so much overlapping of waves. Okay, so as if the waves are not isolated anymore. Okay, so this electron or this wave, he wanted to go in this direction, but then there's another wave which blocks its way, or there are some other I mean many kind of superpositions, or many kind of these overlapping of waves, and this is what actually the actual magic starts with the quantum materials. Okay, a semiconductor is one of them. I mean, semiconductor is indeed one of, I mean, not all the semiconductors, but many semiconductors are indeed quantum materials. Okay, because you can play with that, you can play with that overlapping thing. Okay, if you can, for, I mean, even in standard textbooks we have known that in semiconductors have this valence band and this conduction band, and there is a nice separation between this valence band and conduction band. Okay, but in lab I actually played with a technique called band engineering. Band engineering, can, you can actually engineer this band gap. Okay, I mean, depends what kind of research you want to work on. Okay, in some kind of research, I want to increase the band, so I played, I incorporated something into that structure which is called doping, and due to that the band length increases. In some other cases, for example, sensors. Okay, I want the band gap to decrease, so I incorporated some other kind of impurities. This can be a process of intercalation. It can be a process of doping. So this is all different ways, all different techniques you can play with these quantum materials. Okay, that what make quantum materials interesting.
So the question here is: do you see those quantum materials through a microscope? Can you touch it? Can you feel it? Or how does it happen? I mean, for a layman, if I'm a layman, I'm asking a question. So,
Yes, I mean, so quantum materials. Uh, Quantum materials, I would, I wish I could show you some materials. So the quantum materials is just a normal, I mean structure wise is just a normal material. Okay, you can see those quantum materials. Okay, for example, let's say this ring. Okay, I mean, I can have a quantum materials of this structure. You can see this ring, you can see these quantum materials. Okay, but that does not means that
I mean,
I
see with
that does
naked eye, or through a microscope.
this can materials can be seen through naked eye. I mean, it's clearly visible. Okay, so I can say that instead of this gold, I can come up with this WSE2 ring. Okay, so if I bring it to you, I can show you, Sudeep, see, this is a WSE2 ring. You can feel it, you can touch it, you can do anything. Okay, it's a solid structure. It's a solid structure framework of atoms that you can feel. Okay, it has a mass, it has a weight. Okay, it has a shape, it has a geometry, everything is there. Okay, but what actually defines the quantum property is the way the electrons are behaving. This is what we have to understand. Okay, if the electrons are behaving in a conventional way, for example, in metals, we can see that in metals we have bunch of electrons. Okay, excess electrons. If I connect the metals with a battery, you can make the electrons to flow in the circuit. Okay, but the same things, if I try to do it with my quantum material, maybe I can get an insulating behavior, or maybe I can get something behavior, a certain behavior which is astonishing. For example, the moment I connect it with the battery, some kind of lights or some kind of emissions started coming up from that quantum material. Okay, so it's not just the structure, or not the morphology, or not the shape and size and the geometry that defines the quantumness of the material. It's the property of those, or the electrical property, or you say the magnetic property, or you say the thermodynamic property. That's what separate quantum material from a conventional materials.
Okay, interesting. So, can this quantum thing, right, quantum physics, if I may call it,
Yes.
really affect the gadgets that we use daily, like the laptops, the mobile phones? And if yes, then what effect it will bring to these kinds of gadgets?
So I mean, so if I remember correctly, Sudeep, the first computer which we had in the year 1945, it was named as ENIAC, ENIAC, Electronic Numerical Integrator and Computer. Okay, and this was a huge machine. Okay, it spans at the area of 1800 square feet. 1800 square feet is kind of a 3 BHK apartment nowadays. Okay, so it weighs like 27 tons, and there are like 70 thousands of capacitors, resistors. It's a huge thing. But now you have a computer, something like on phone, something like on your smart watch, something like in your goggles, something like in your laptop. Okay, so why this evolution started, I still remember. I mean, when I was in my class 10 standard, my teacher used to say that please do the calculations nicely. I mean, you can never have an access to calculators all the time. You have to do the calculations very fast. Okay, but that was not the case. Now you have the calculator in your pocket, right? So what changed? The I mean, what changed? It's only the quantum mechanics that changed the entire picture, the entire game. Okay, so now you talk about transistors, for example. I mean, those computers, or those, I mean, every computer is made up of transistors nowadays. Okay, so you can have like billions of transistors in just 1 centimeter by 1 centimeter IC chip. Okay, so I mean the GPS, right from the GPS, right from the medical imaging, right from the, if you talk about lasers, if you talk about smartwatches, if you talk about kitchen microwaves, if you talk about washing machines, everything you have this small controller, microcontroller, which is governed by this quantum mechanics, principles of quantum mechanics. Okay, so quantum mechanics indeed plays a huge role. Okay, this miniaturization, so miniaturization means you try to shrink the size. So now you have a sensor that can sense your heartbeat. Okay, how long is the, how large is the sensor? Maybe it's a millimeter size sensors. Okay, so how this millimeter size is possible? Because of this quantum effect. Okay, because ultimately we have to understand that the advantage of these quantum materials particularly is that you can go as thin as possible. That means you can go to a level of thinness which is kind of atom thin. Okay, a dimension of an atom. Okay, a dimension of an atom, how big is an atom? Atom is, let's say, maybe an Armstrong in size. One Armstrong is 10 to the minus 10 centimeter. Okay, but I mean, still we could not, I mean, we could not reach that that level of thinness because of some other problems. Okay, so that's what, there was a famous, I think he worked for Samsung or Siemens. uh, uh, what his name, Betty Moore or some Moore. We call it Moore's law. I forgot his first name, Betty Moore or Gordon Moore. Okay, so Moore's law says that you come up with, so in every 2 years the number of transistors that you put in a 1 centimeter by 1 centimeter chip will double. Okay, so that means you keep on increasing the density of the transistors. So that is the level of technology we are having now. Okay, but then you cannot do it for infinite period of time. So in that 1 centimeter by 1 centimeter, you keep on putting the transistors. At one instant, what will happen? You will have so many transistors, and then the effect of interference start coming into play. Okay, so one transistor will affect the other transistors. Every transistor dissipates some amount of heat. Okay, so the heat dissipated by this transistor can affect the neighboring transistor. Okay, so ultimately that will break down the Moore's law, and that is where actually these quantum materials generated. Okay, earlier people were happy with the silicons and germaniums. They were the major, I mean, they were the major powers of this silicon revolution or this semiconducting revolution. Okay, nowadays people are replacing silicon with this WS2, MS2, many other interesting graphene. It's a super material. Graphene is one of the super quantum material. Okay, the only disadvantage with the graphene is that the graphene, this, if you remember the band gaps which I was talking about. Okay, the band gaps is missing in graphene. Okay, so when you don't have the band gaps, you cannot control it well. For instance, in one case, I want the graphene to be an insulator. In other kind of research, I want the graphene to be a conductor. But then you cannot play with the band gaps. So that's what the graphene fails. And then the picture of other quantum materials came into effect, where you can actually engineer the band gaps of these quantum materials.
Okay, very interesting.
Yeah.
So uh, let's move on. And I
Yes.
have two questions bundled into one. What is the most interesting quantum experiment that you have worked upon? And did the results shock you? Or what experiments did you conduct, the results of which maybe shocked you, that you never w- like saw that kind of a result coming out? Because quantum, we are still experimenting, right? We don't know what will be the outcome and all that. So from that angle.
Yes, Sudeep. I would particularly remember when I was doing my PhD. Okay, when I was doing a PhD, I was working in some nanocomposite systems. It's called the percolative nanocomposite systems. Nanocomposite systems, you can imagine, is we were working, just by the name you can understand that we were working with some materials which is of nanometer size. So particularly the quantum, these quantum objects. Okay, so then, I mean, in the world of percolation, I mean, let me understand, I mean, make you understand what is percolation basically. Okay, percolation is all about the geometrical connectivity. For example, let's say you want to go from your home and leave for your office, and between your home and office there are potholes. Okay, if there are two number of potholes in between your office and your home, you cannot reach your office, because you can drop yourself on the potholes, you can hurt yourself, you can do anything. But if the number of potholes are limited, not limited, let's say, yeah, very limited, let's say three potholes, four potholes, you can easily manage to reach your office by multiple routes. Okay, but then there is a picture which lies in between. Okay, so you can have a critical fraction of potholes which can limit your way. I mean, you will be happy and you will be not happy at the same time. Okay, so right in that limiting region, that means only at the critical fraction of potholes, Okay, either you can reach safely, or I mean there's an uncertainty. Okay, or you cannot reach safely. Right in that intersection, you can have many interesting quantum phenomena that can take place in our quantum materials. Okay, so people have been working on this speculative nanocomposite systems for a long time, and luckily people have came up with the idea that mostly all those behaviors shows a power law behavior, which was I'm not going into details. I will just tell you some values. So the power law behavior of, let's say, power with an exponent 2. Okay, it was a standard form. People were getting in many nanocomposite systems. They were always getting whatever kind of measurements they were doing electrically. They always get that power too. But when I did the experiment, when I was totally into these nanocomposite systems, okay, I got a fraction much, or I got a value much lower than 2. It was like zero point 0.6, zero point 0.7. At one point, I was really doubting myself where I'm doing wrong. Okay, I never communicated my results to my guide. Okay, I was simply thinking that why I'm doing wrong. I was again going back, doing some more literature studies, and again redo the thing, and again I was coming back with the same value around zero point 0.6 to zero point 0.8. And then later, when I frustrated, I went to my guide and saw I told the entire thing. Okay, he said me that, "Rupam, don't worry. I mean, you go ahead and repeat your experiment. Once again, you repeat the experiment." I told him that I repeated many times, and he told me, "No, you repeat another 2 times. Don't worry." Okay, and eventually when I repeated, I got the same number. Okay, and then he actually told me that this is very interesting. People have been getting the same number for a long period of time. You are getting something different, so something is there in your system which is not in present in the other system. Okay, and it was a very very interesting study. We and it took me like 8 9 months. I mean, apart from collecting the experimental data, it took another year to understand what is happening with my system. And eventually it got published in a good day, I mean good paper. People came up with some strong reviews on that article, but eventually they accepted. Okay, I mean, and then I remember my guide called a scientist from Israel. He was a very big physicist in that field, speculative field. Okay, and when he came there, he discussed the results with him, and he appreciated a lot. I mean, he told that yes, we are all indeed working with the same thing. Okay, so that break, I mean, those that universality that always you should get a value of 2. Okay, is not true in some sense. In some nanocomposite systems, you can have a value which is greater than 2, or you can have a value which is less than 2. Okay, but we were the first one who came up with some different data. That was quite interesting, and that actually threw me out. I mean, I mean, my friends, my colleagues, my teachers, colleagues have a lot much serious discussions on these things. And yeah, I mean, this is how it goes. I mean, that you correctly said one thing, Sudip, that I mean, quantum is such a thing. One experiment is not sufficient. Okay, I believe many reputed universities came up with the same fallacy, or fell into the same trap. The moment they found, I'm not naming any institute, the moment they found some out of the picture results or out of the box results, they found that it's a very interesting thing. Okay, but you have to understand that every instrument comes with some artifacts. Okay, not humans have built the instruments, so humans are not error free. So are the instruments. So you have to do, or you have to make the practice of reproducibility, so that you can reproduce your result. Okay, and then only you go for publication, or then only you can go to the forum where you can discuss with your peer groups. Okay. So I remember when I was doing my PhD, I indeed, when these results came, my professor told me to attend American Physical Society. It's a big conference that happens in Chicago. I mean, that happens everywhere. I mean, every year they choose different locations. But in my time, I went to Chicago, and I attended that meeting. And then there in that conference, I was told by my supervisor to give a oral presentation. Okay, and when I was giving the oral presentation, at the end of the oral presentation, there was a professor from Tohoku University. He was a Japanese guy, a very big shot. And he came in and he politely approached me, and he actually did not challenge me. Okay, that the work which I presented is totally his work. His domain. He has worked in that domain for his entire life. Okay, so I'm talking to a person who is super expert. Okay, but then he came and he sat with me with a coffee, and we had a 2 hour discussion. Okay, and then after he called my guide, and many things happened, and then he actually invited me to his university, which unfortunately I could not go. Okay, but this is how, until and unless you don't communicate your results, this is also one of the major part. Not only getting the results is important, you have to communicate your results. This is what I want to project, okay, to any young researchers. Okay, there are people who have been working all night, all day and night. Okay, but while publication comes, they are very lagging behind. Okay, so my opinion is that if you are getting a reproducible results, it does not matter if the results is new, you publish it. Okay, you see what other people think about your results. Okay, in this way you can continue your work. This is how we do, this is how I learn, and this is how I still do in this. Till now I do the same process, or
Yeah,
I follow the same
interesting.
process.
I mean, until and unless you publish, people will not know. People will not reach out to you. They will not discuss with you and share their findings, which will lead to ultimately the progress of whatever theory you are working on, whatever process you are working on. So that's how humanity
Absolutely.
also progresses, right? Okay.
Absolutely.
So moving on, I have a question, and a lot of people have this question, right?
Yeah.
So it is said that whoever breaks this quantum thing, right? Quantum uh, paradox, maybe, right? That country is
Yeah.
going to become the next superpower. Everybody is chasing China, US, Russia, Japan, Korea, India. I don't know about India. Maybe you should tell us about how India is doing, because next big thing, as far as I know, is quantum computing, and people are waiting for a big breakthrough, right? Can you
Correct, correct.
share your thoughts on that, or like where are we progressing in India's stand? Where are we in respect to the other countries in the world? If you have anything to share on that.
Yes, yes, Shudip, definitely. So, understand one thing, that this quantum uh, information, it has 4 pillars basically. Okay, it has quantum computing, it has quantum communication, it has quantum sensing, and it has quantum materials. Okay, so these are the 4 pillars. So China is undoubtedly the sole leader of the quantum communication part. Okay, so they are so much advanced. If I remember correctly, they in the year 2016 they have their first satellite-based quantum communication. Okay, in Milius, I believe it's a project called Milius, and they are still getting data out of it. They are taking it to the next level. Okay, so before I jump into these things, let me understand. Let me tell you briefly that why we suddenly started talking about this quantum computing. Okay, so understand one thing, that classical computers, whatever computers which we are having now, okay, it is growingly, or it is becoming incompatible with the amount of data which we are playing with nowadays. Okay, so for example, these pharmaceutical companies, for example, the pharmaceutical companies, or any other things. Okay, so any other things. So I would say that quantum computing is something which will actually make the work more easy in sense, the classical computers which were incompatible with that loads of data will be easily processed very fastly, okay, or very securely when we jump into the quantum computers. The only reason is that The quantum computers, in quantum computers we are dealing with qubits. Okay, so qubits is kind of a same. It's an elementary. It's an elementary entity which carries all the information. So very much analogous to the classical bits, the binary bits which we have, this 0 and 1. But what makes different in the quantum bits is that along with 0 and 1, there can be a third state which is 0 and 1 simultaneously. Okay, so again, I mean, to understand this thing in a very simple way, I would say, for example, so this is called the superposition. This principle is called the superposition principle. That 0 and 1 is two separate states, and then you have the third state, which is basically the combination of these two states. Okay, for example, you are a son of someone and you are a father of someone. Okay, everyone is, I mean, is having a dual character. Okay, so we are into a superposition state. Okay, to be in a layman's word. Okay, so what, so this itself, this superposition changes the entire ball game. Okay, so so mathematically what we say is that, I mean, if I want to explain this mathematically, the the or the superposition states, um, no, I won't go into details this mathematically. I mean, this is not the right platform to go into mathematics. Okay, but understand one thing. For example, the power of the classical computers. Okay, if I want to simulate a quantum system is basically a collection of, let's say, in a simplest, in a very simple view, a quantum particles can have, each 100 particles can have either two types of spins, spin up and spin down. Okay, so if you have, I mean, each particle have two such directions, so in that case you will have 2 to the power 100 different states, 2 to the power 100, since you are dealing with 100 such particles. For the classical computers, this is kind of an, the complexity of this problem grows exponentially. If I want to take help of a classical computer, I can take help of one, or I can add one more bit. I can take help of one more bit to solve that problem, but that bit will actually, that bit will not fasten the process. Okay, what I want to say is that the power of the computer will grow linearly, but the complexity of the problem will go exponentially. You cannot tackle a problem which is growing exponentially with a linear capability power. Okay, but in the case of quantum computer, it's totally different. Okay, since you have you have a superposition states. Okay, you can utilize both 0 and 1 simultaneously to process something. Okay, so to process or to create that quantum state, I can use both 0 and 1 simultaneously to do that same process. So it will be much more faster than a classical computer. Okay, so the parallelism or the fastness, all these things are possible in the quantum computers, but not possible in the classical computers. This is the first thing. Okay, now, I mean, if I take a good example of this quantum computing, I mean, I mean, good application of quantum computing, I can think of this quantum cryptography. Okay, so what is cryptography? I mean, cryptography is nothing new to us. I mean, the way we are chatting to each other, or way we are texting the message, so everything works in some crypto, in some crypto ways, or some crypto channels, encrypted channel, we call it as encrypted channels. Okay, so encrypted channel means your personal message is getting encrypted by some public key, and the receiver can read your message through some private keys. Okay, and the mathematics behind this, all this all this way of communication was built, I believe, in the year 1977 by three guys called, uh, by three guys called Ron Rivert, Adi Shami, and um, Leonard Adelman. If I yeah, we call it RSA algorithm, RSA algorithm. So entire crypto system or entire the way of communicating the message encryptically and we decrypt the message. Entire thing is formulated on that RSA phenomenon. What does RSA do? RSA basically take your message and then it mathematically it factorize into prime numbers. Okay, so it factors into prime numbers and then it sends it. Okay, and the private key which you have, they know how to decode the things and they come up with the same number which you actually factorized into other prime numbers. Okay, so this is how you do the things in a normal way, in a normal classical computer. But in the case of quantum computing, okay, you cannot you cannot you cannot steal the data. Okay, for example, in this RSA algorithm, if I'm clever enough, I can break the things with the help of quantum computing. Okay, why? Because quantum computing can use 0 and 1, and it can easily it can you can actually engage both the bits simultaneously to get the factors. Okay, you understand what the factors mean, right? For example, 24 and 46. 24 and 46, the common factor is, let's say, 2 is a common factor. Okay, so but so this 2 is the common factor. So I'm just taking an example. I mean, I'm not talking about like 3-bit numbers. I'm talking of a number which is like 256 bits. That long numbers. Okay, have to understand that you are factorizing that bit numbers. Okay, so those numbers uh, can be factorized very much easily, much precisely, with the help of quantum computers, and you can actually break into the system. Okay, so whatever encrypted and decrypted message you were happily sharing with, if I'm having a quantum computer, I can easily log into and I can break the things and I can see the things. Okay, which is not impossible, which is not possible with the classical computers. So this is one of the application. The other application is the pharmaceutical companies. Okay, if you want to digitalize the molecules, how the molecules behave. Okay, for I mean, classical computer can get, I mean, it can store the data of one molecule at best, or let's say two molecules at best. The moment you come up with three molecules, there will be interaction between first and three. There will be an interaction of proton and electrons of the neighbor. There will be interaction between electrons and electrons. So many informations are gathering up. So the classical computer will eventually fed up with these informations. Okay, it cannot store this, it cannot process this load of data. Okay, but quantum computer, you are leveraging the principle of quantum physics or quantum principle, that is the superposition principle, and you can make good use of that. Okay, so digitalizing a molecule, or having a secure way of communication. Okay, so interestingly, you can break the RSA algorithm, this message communication, but you cannot break a quantum communication. Okay, you cannot. For example, if I am you are exchanging the message through quantum communication or through quantum channels, if there's a third party that wants to interfere, the moment he or she interferes, I will come to know that someone has interrupted and I can lock the message. Why? Because because again, it's the principle of superposition. Okay, I myself don't know whether the electron is up and down. Electron is in superposition state. Okay, so if I know that I'm sending you up spins, you should end up having up spins only. Okay, so then any third party can come in and they can say that it's an up spin and they can play with the data. They can steal the data. But when I myself don't know which is up and down, because I am starting with something which is in superposition state. Okay, the moment, because something you started with which is unknown, which is a probable thing, How can a third party come and knows the thing? Okay, so this is what make this is there is a theorem called no cloning theorem. Okay, through no cloning theorem, it says that you cannot decrypt a message which came out of quantum wave or quantum channels. Okay. Yes, I mean there are
So
many other things I can talk about. I mean there's endless things. Okay, but I
yeah,
mean
yeah.
this is the
So time
yeah,
slew actually. I mean, it's
yeah,
already more than 1 hour that we have been discussing, and it has been
yeah.
so enriching and so interesting. So, but unfortunately, we have to stop. But I won't let you go without asking last two questions for the day.
Yeah, sure. Yeah, sure.
One is, if Einstein was alive today, seeing the progress that we are making in quantum, what would he think, and what would he still keep on arguing that this is? Because initially I know that he was not very, I mean, averse towards quantum and all that. He said, no, no, it's not possible, and all those things, until that the Schrodinger cat experiment came in front of him, right? So as far as I know, maybe you can elaborate on it more. So if he was alive today, how would he see that? I mean, what is your thought on that?
Yes, I mean, yeah, definitely. Whatever you said is absolutely correct. Even the Schrodinger, I mean, Schrodinger, who gave the wave nature of this, I mean, the mathematical wave treatment, he even didn't like the idea of this entanglement at one point. Okay, so what you are talking is all about the entanglement. Okay, entanglement means, I mean, if I'm having two electrons which are far apart, I mean, does not matter whether it's in Earth or the other particle is in Mars. If I change the state of one electron, the automatically it will change the other state of the electron. Okay, and in other ways you can say that if I'm having an entangled pair, let's say both the spins are up. So if I'm having up spin, I can 100% know that you are also having an up spin. The moment I change the direction of the spin, I am 100% sure that the spin at your end has changed. Okay, so this is called the entanglement. Again, in the I would say that in the the nature, this quantum nature is inherent in inherent in the surroundings. For example, if you might have heard of twins. One of the twin is sitting here, the other twin is in some other place. If he gets sick, the other twins also get sick. I'm not talking about all the twins, but mostly it happens. Okay, so you can say that they are entangled. Okay, whatever happens to the first guy, it will happen to the other guy. Okay, the same things. I mean, similarly, you can think of the electrons having this entanglement. Okay, so what Einstein actually did not like the idea. It's a famous paradox which is called the EPR. Einstein was one of them. Boris Podolsky, and then Nathan Rosen. Okay, EPR. So what does EPR says that it says that you are that it violates the principle of there are two principles which is violating the entanglement theory is violating two principles. One principle is called the principle of locality. So what does principle of locality says that you cannot transmit the information faster than the speed of light. Okay, for example, if this is spin up, it has to spin up. If it is going spin down, so the process of transferring this information is impossible. That means you are challenging the whole theory of relativity, general theory of relativity. Other thing is that if you are changing this from up to down, this is also changing. Does not matter whether it's in Mars or this is in Saturn or it is in some other planets. Okay, so that means you are violating the principle, the local principle. That means the environment can be changed only by the mere presence of the closest interaction. Okay, that means I can change this spin only when if there is certain disturbance that has happened here. You cannot change arbitrarily. I mean, some disturbance have to be there due to that changes happen. This is what principle of locality. The other principle that he challenges is the principle of realism. Okay, so that means when you are saying that this is how this is spin up, this is also spin up, that means there is a property which is already inherent. You cannot predict on something which is 100% sure. Okay, when you are turning this down, this is also turning. That means you are predicting 100% that it will be turning down. That means there has to be a hidden variable That has to be a hidden variable which is unknown to us, still unknown to us. Okay, so he did not like the. So it's false to say that Albert Einstein did not like the idea of quantum mechanics. He did not have problem with the the concept of quantum mechanics, but he challenges that the quantum mechanics is some form of an incomplete formalism. Okay, that means we are missing some hidden data, hidden variables. This is what he was all unhappy about. But later in 1960s, I believe, major big experimentalists like Alan Aspect, there's another called Bell's inequality. These two people came up with the experimentals and theoretical foundations, and they clearly say that quantum mechanics is a full theory. Whatever theory we know, it's totally full. There is no hidden variables associated with quantum mechanics. Okay, and that was clarified later. That was clarified, and then I believe actually this quantum computer was coined by Richard Feynman. He gave to MIT. He was presenting some of his work in a conference at MIT in 1981. There he first talked about that to understand the nature or the quantum nature, you have to get a quantum computer. So this is actually the date from where people have started focusing on the quantum computers. Okay, so it has huge applications. I mean, now it does not matter who likes it, who does not like it. It's coming in our way. Okay, but frankly speaking, the computers which we are using, the classical computers, the quantum computer is not going to replace the classical computer. Many have a wrong notion that it will take our jobs. It will take the no, it's not going to take the jobs. Okay, it's coming because to make our life easy, because now we are, even in India we are having 1.4 billion people. 1.4 billion people means so many datas. Classical computer cannot handle those. Let's say you are keeping a track of other data. Okay, some people are coming, some people are dying, some people are forging. So many things can possibilities can happen. Classical computer cannot keep track of all these things. Okay, all these priorities. Okay, but quantum computer, since it has a principle of, it can use the principle of superposition and entanglement, it can happily deal with this kind of complexities. Is it clear?
Yeah, yeah. So quantum
Yeah.
computing is a necessity for India, if I understand you correctly, and the way the population is growing to handle the data and all that. So it's a necessity for the future.
By the way, India has progressed a lot on this quantum. It has recently quantum computer with 25 qubits they have generated. Okay, India. China is leading us. China has now at present China is having playing with 500 qubits, or maybe they have a program increasing from 100 qubits to 500 qubits. USA quantum these quantum processors or Sycamore processors, they already started with 54 qubits long time back. 2019, they declared the quantum supremacy. I think Google, but IBM, Google, Microsoft, these are the now the big players. Okay, so for the quantum computing, I mean, it's a fact, Sudhir, that country who is having a more percentage of GDP invested in research, they are going to get the final game, or they are going to get the final laugh. Okay, so quantum computing does not come free of cost. It's a huge investment. Both government, both private players have to come together, okay, and have to deal with it. That this is what USA, UK, they are doing. You see all the developed countries, they have their they have their negotiations with AI. They are coming, they are making shaking hands with this quantum computing, these nuclear energies, AI, nuclear energy, quantum computing. They are all doing this in a partnership mode. Okay, so India should not lag behind. I mean, India have a huge talent of engineers and physicists, so and chemists, scientists basically. And I believe India is doing is going in a right way.
Yeah, yeah. So, but India. I mean, the infrastructure needs to be a little bit improved because we are not a very research-oriented society, and historically we have not been very good in doing researches and coming up with new products and technologies. But things are changing, and hopefully for the better. Uh,
Correct,
Who
correct,
knows?
correct, 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 correct.
So, last question of the day, and I
Yes,
need your one word answer for this. Okay. So, if quantum
sure.
mechanics is a movie, which genre would it fit best? Is it a mystery? Is it science fiction, comedy, or a scary movie?
I mean, okay. I mean, since you wanted a one word, I would say science fiction would be a good one. Okay, but again, a combination of comedy. It can be in superposition state. Okay, comedy and science fiction both. Okay, serious and this is what quantum mechanics is about. I mean, always in a superposition state. Why not here also? Comedy and seriousness both. Okay, but yeah, I mean, this is what the youngsters, the today's youngsters have to look for. I mean, yeah, if you want to understand quantum mechanics through a movie, through a comic show, or through some simple experiments, do it, go for it. Okay, so this scientific department needs to build up within this young community. I mean, young students, just not rushing for marks for clearing these competitive exams. This won't work. Okay, I mean, all the developed countries are developed not for the reason. I mean, not for a reason that they are having high quality. The high quality students does not need to have a good marks. Okay, I mean, you can have if you have a scientific department, if you can think on a problem, particular problem, you can do much better. Yeah,
Yeah, true. So, we can call then quantum mechanics, quantum physics, quantum computing, uh, a comedy science fiction, maybe, to end it all, to end
yeah,
today's discussion.
yeah. And Chacha
Okay.
Jojuri should be there. He's my favorite comic. Chacha
Yeah,
Jojuri shooting a
definitely.
laser gun, quantum gun.
Yeah, yeah. That would be very interesting.
Yeah,
So
yeah,
thank you so much. It has been very engaging and very, informative. And I learned personally a lot of things from you. So thank you for that. And hopefully the viewers will also learn a lot of things, and they will also be interested in this topic, take India forward, because what you said, this is going to be the future. And with India's population growth, the country size, everything,
yeah,
quantum is
yeah.
going to be the future. So I wish you all the best for your upcoming experiments and research work. Thank you once again for coming to the show, and it has been a really honor and a privilege for me to host you. Thank you so much.
Sudeep, again, thank you so much for welcoming me in this show, and you are doing a wonderful job. Okay, you are inviting people from all walks of life. Okay, people really want to know. I mean, the how common people thinks. Okay, and you are doing a good job, and that will definitely. I mean, this kind of things, podcast will definitely benefit me, and I hope to. I hope you to come up with many other shows I will get so that I can log into the screen. Okay. Thank you, Sudeep. Thank you.